What's up, everybody? It's Dan from SageMathTutoring.com, and we are back with another video. And this time it's for a student of mine who is taking, obviously, a math class, algebra class, and the topics we're going to cover right now are off of his review sheet, and it's really two topics. It is classifying various numbers and also literal equations. Now, we're going to start with a few classifying numbers problems. And what I did was I made a nice sort of sheet here. This is kind of, maybe it's not that nice looking, but it's functional for sure. So the bottom line is um, real numbers are basically all the numbers on a number line. Now, as is the case with my student, um, he has yet to get into imaginary numbers, because when I talk about real numbers, you might be wondering, okay, well, what isn't a real number? Well, that would be imaginary numbers or complex numbers. And we're not going to be talking about those today. Safe to say that all the numbers on a number line, though, any conceivable number on a number line would be considered a real number. So the real numbers encompasses all of this other stuff. Now, one particular family of real numbers is called irrational numbers. And some very famous irrational numbers are radical 2, radical 3, pi. And these always result in a weird decimal. For example, pi represents in the weird decimal of 3.141592653, whatever. And there's no repeating pattern here. So this goes on forever. The decimals go on forever, and there's no repeating pattern. So I would even say this looks sort of crazy, okay? It looks irrational, okay? So that's the way to sort of think about it. Now, irrational numbers are such that you cannot represent them as a fraction where you have an integer over an integer. You cannot represent them as an integer over an integer. So we're going to discuss what that means in a moment, but I'll put a little cross through there. Irrational numbers are such that you cannot represent them as an integer over an integer. To avoid confusion, I'm going to erase this right now, but I just want you to understand that, okay? If it's irrational, it cannot be represented as an integer and over another integer. It's also the case that if you were to convert any irrational number into a decimal form by perhaps putting it into your calculator, like taking the square root of 2, well, the decimal would repeat forever. So continuing our overview of this sheet, we already recognize that there's real numbers and then there's irrational numbers, but then there is all this other stuff. So in a way, you're better off thinking about real numbers as being composed of irrational numbers and all the other kinds of numbers. Now, the other kinds of numbers I am separating with a chasm of separation. Okay, so I'm going to kind of darken that for now, just so we really see that that's where the difference is. You have irrational and then you have all this stuff. Now, the overarching category is called real numbers. We already discussed that there's irrational numbers. Well, obviously, there's going to be rational numbers. If there's irrational numbers, then the next overarching category over here is rational numbers. Now, I'm going to talk about rational numbers, but let's be very clear first, actually, about integers. We're going to really take a look at the integers first, okay? So integers are whole numbers, including 0 and including the negatives. So that could be like -2, -1, 0, 1, 2, and 3. These are the integers. Notice how 0 is an integer. Now you do want to be careful, because even something like radical 2, like square root of, or radical 16 rather. So square root of 16, that's a radical 16. Well, that is an integer because the square root of 16 is 4. So therefore that is a whole number. Therefore it is an integer, okay? And not only that, but it's a whole number that happens to be, somewhere on the number line, one of the tick marks on the number line, in other words, okay? So that's what integers are, and here's a nice list of examples to give you an idea. Notice again how 0 is an integer. Now, we're going to move up to this other category. Now, the bottom line is integers are part of a larger family called rational numbers. Rational numbers are any number that could be represented as an integer over another integer, okay? Now, an example of that would be 3 over 5. That's an integer over another integer. Another example would be negative 2 over 1, right? Another example would be 6 over 7. But check this out, though. You have negative 1, 3, and 5. Those are also rational numbers because the truth of the matter is that 5 is secretly 5 over 1. 3 is secretly 3 over 1. Negative 1 is secretly negative 1 over 1. So therefore, these sort of integers here could also be represented as an integer over an integer. It's just that the integer underneath them is 1. Okay, so that's the case with rational numbers. Now, I also wrote here that let's say you had a fraction like 6 over 7 or something like that, and you figured out what the decimal version of 6 over 7 was, you might get some weird decimal, but at the end of the day, the decimal is going to be kind of like a nice looking decimal where the pattern of decimals repeats forever, like 77777 forever. Now we want to make sure that we can see the difference between something like that and the irrational numbers that we were talking about before, where it's obvious that the decimals are a big mess over here. Once again, it's irrational, okay? So you might get a decimal when it comes to the rational numbers. You might get a decimal, but it's going to be a nice looking decimal, okay? So anyway, that's really the overarching category. I know I talked about integers first, but integers are part of a family of the rational numbers. And backing up a little bit, once again, just to give you the overview, real numbers are all of this stuff, and there's two main categories, irrational and rational. Now, we already discussed rational. We also already discussed integers. Integers are a kind of rational number. That's why this sort of integer landscape is inside the larger rational number landscape, okay? So integers are a kind of rational number. Now, we also have a special kind of integer called whole numbers. Now, whole numbers are all of the counting numbers, including 0. Okay, whole numbers are all the counting numbers, including 0, and they start with 0, and then it goes up from there. So obviously, the big difference between whole numbers and integers is the fact that there are no negative numbers when it comes to whole numbers. That's the first time we get a nice cutoff where there's no more negative numbers, starting with whole numbers. Now, a certain special kind of whole number is called natural number. Now, natural numbers are the same thing as the whole numbers except without the 0. It's 1, 2, 3, 4, 5. Now, natural numbers are the numbers that show up in nature. You know, like you could say I have 1 apple in my basket, I have 2 apples in my basket, I have 3 apples in my basket, right? We use these numbers to count like actual things in the world. If you have 0 apples in your basket, you don't really say that you have I have 0 apples in my basket. You don't say that. You just say, oh yeah, here's a basket. It's an empty basket. Okay. So natural numbers are the numbers that we use to count objects. Okay. Whole numbers include 0. Anyway, that's my brief overview of the different categories. We're going to leave this reference guide up and we're going to answer a few questions. Let's start with this one. Indicate whether the statement is true or false. 0 is a negative integer. Okay, now I actually haven't mentioned this. 0 is a special number in the sense that it's neither positive nor negative. Now let's be very clear. 0 is an integer because the integers are over here and here's 0, right? Integers are over here and here's 0. So 0 is most definitely an integer, but it's not a negative integer because one way of saying it is that there's no negative sign in front of the 0. Okay, so it's not negative. 0 is neither positive nor negative, and that's the only integer that we can say that about. Okay, so when they say 0 is a negative integer, well, guess what? Hold on, wait, hold on. That is false. All right, moving on. Okay, we still have a reference guide. Tell which set or sets of numbers below belong to. Set or sets the number below belongs to. Natural numbers, whole numbers, integers, rational numbers, irrational numbers, or real numbers. Now, I didn't say this in the last slide, but if you want to try to answer this yourself, go ahead, pause the video now, and try to answer it. Okay, so now you have unpaused it, or maybe you never paused it, but that was the moment where you could have paused it, and we're just going to talk about the problem now. So we have 7 over 9. Well, let's take a look. Is it rational? Well, absolutely. It's totally rational because it's represented as an integer over an integer. Now, it turns out it looks like there's no opportunity to write rational. Maybe we'll just focus on the answer choices. Is it a natural number? Well, let's look at the natural numbers. Well, those are the counting numbers. No, these are all whole numbers. These are all like 1, 2, 3, 4. No fractions here. So it's definitely not a natural number. Is it a whole number? Well, the whole numbers are the same thing as the natural numbers, except it includes 0. So definitely not a whole number either because there's no fractions in the whole numbers. 7 over 9. Is it irrational? Well, irrational would be down here. And do you remember how I said it's not allowed to feature an integer over another integer? I said that earlier about the irrational numbers, right? Irrational numbers, you are not allowed to have integers over integers. Well, this is an integer over another integer, so there's definitely no irrational, it's definitely not an irrational number. Is it a real number? Well, yes, 7/9 is a real number because a real number is like all this stuff, right? And that includes the fractions, like rational numbers, fractions. So that's the answer. Moving on. Tell which set or sets the number below belongs to. Natural numbers, whole numbers, integers, rational numbers, irrational numbers, or real numbers. Okay, so 615 is the one that we're looking at now. Please pause the video if you want to try this yourself. Figure out which one of these is going to be more than one answer choice, okay? Pause the video now and give it a shot. Okay, so if you tried that, hopefully you went one by one. You started with natural numbers and you asked yourself, okay, well, is 615 a natural number? Well, the natural numbers are the counting numbers. It's all the positive whole numbers there. So there's no question that 615 is most definitely a natural number because it's positive and it's a whole number, right? And you can kind of see these dots. That means it goes up from 5, right? So it goes definitely would eventually get to 615. Is 615 an irrational number? Well, the answer is no, because 615 could totally be represented as 615 over 1. And that is an integer over another integer. And once again, like I had said earlier, you're not allowed to have integers over integers when it comes to the irrational. I'm just going to leave that there. Not allowed to have integers over integers. Okay, so definitely not irrational. Is 615 an integer? Well, the integers are over here, and the integers are all the tick mark numbers that would be on a number line, 0, 1, 2. Also the negative numbers too, okay? So integers would be all those tick marks, and 615 would most definitely be one of those tick marks. So we're going to say that it is most definitely integers. Is 615 rational? Is 615 rational? Well, rational number is any number that could be represented as an integer over another integer. That's part of what being a rational number is. Well, I already discussed how 615 could be rewritten as 615 over 1, and that is most definitely an integer over another integer, 615 over 1. So is it rational? Yes. Now the next question is it a whole number? Well, whole number are all the counting numbers, but also 0 is in the list. Now, we had already discussed that the counting numbers would include 615, so these whole numbers would, of course, include 615 as well. So it is a whole number. Hopefully that makes sense. Moving on. Okay, so tell whether the statement is true or false. A number can be both whole and positive. So go ahead and pause the video now and give this one a shot, and I will meet you in 5 seconds on my end. All right, so maybe you paused the video, maybe you didn't. One way or the other, let's look at it. So a number can be both whole and positive. Well, here's the whole numbers, 0, 1, 2, 3, 4, right? I don't know. I see plenty of positive numbers. Here they are. All these are positive. So the answer is true. Yes, it can be, a number can be both whole and positive. All right, so moving on from this. Okay, indicate whether the statement is true or false. The square root of 22 is a rational number. Okay, so go ahead, pause the video now, and we'll meet again soon. All right, so maybe you paused it. And if you didn't, we're just going to get right into it. So square root of 22 is a rational number. Is that true or false? Well, it turns out that that is false. And the reason is because it is irrational. Now, the reason why it's irrational is because if you were to plug a radical 22 or the square root of 22 into your calculator, you would get 4.69041575 dot dot dot. So as you can see, these decimals here are, we can say these decimals here are a mess, okay? And we'll say it's a crazy mess, all right? Look at this. It's ridiculous. I don't know what's happening over here. Big crazy mess, and whenever we have a crazy mess with decimals, we can associate that with irrational. All right. Now, I am going to say something that is worth thinking about or considering. Another way you know you're dealing with irrational numbers is if you have a square root of something, but it's not a perfect square. Like before, we had the square root of 16, and that is a perfect square. 16 is a perfect square. And the way that we know is because when you do the square root of it, it gives you a nice, beautiful, clean whole number there, okay? But when it comes to something like the square root of 5, well, 5 is not a perfect square, so that's going to give you a wacky, crazy decimal. Every square root number that is not featuring the square root of a perfect square, that will be irrational. So whenever you see a square root number like this, you're going to want to be on the lookout. You're going to be like, okay, it might be irrational. Let me just double check. Is 22 a perfect square? Is there a square root of 22 that would give me like a nice clean number? Well, if there is, then it would be an integer, okay? But if there's not, then it will be irrational, and that is exactly what happened here. With the square root of 22, we ended up with a decimal that turned out to be a big crazy mess. So big crazy mess means it's irrational. Okay, show that 262 is rational by writing it in the form a over b, where a and b are integers. So go ahead, give that a shot, pause the video if you wish, and try that one, and we will meet soon. Okay, so hopefully you paused it and you recognize that, well, 262 is most definitely rational because it could be written such that there's this invisible one underneath it. So in reality, you could think of 262 as like a fraction kind of, where 1 is in the denominator. And in that way, we just morphed it or we turned it into this particular form where it's like a over b, where a and b are integers, integer over integer, okay? Well, that's what we did. And that is exactly why this is the answer. And guess what's not the answer? Any of this stuff, okay? All of that is gone. All of this is wrong. None of this stuff equals 262. The only one that actually equals 262 is that one. And this one is written in the form where it's 262 over 1, an integer over another integer. Okay, so moving on. Okay, so this is the first time where we are dealing with a different kind of problem in this video, and that's literal equations. Now, literal equations are such that you have an equation composed largely of variables like p, r, t, and s, and they ask you to solve for one of the variables. In this case, they're asking you to solve for r. So in other words, they want you to get r by itself. So it's like r equals all the other stuff. You want all the other stuff over here. Now, I'll invite you to pause the video now if you want to give this one a shot on your own before I explain it, and then we'll go over it after that. So go ahead and pause the video now, and we will meet soon. Okay, so maybe you paused it. One way or the other, we're going to get right into it. At the end of the day, first of all, it's actually a good idea to rewrite the equation. I'm going to put r in blue because I really want to draw attention to it. Now, my t's, I understand, look weird. My t's look like a's, kind of. But it's just a cursive T, and I draw it that way. That way it looks a little bit different than the plus signs, okay? I don't want to confuse it with a plus sign. Now, at the end of the day, we want to get R by itself. Now, in this sort of computerized program, they put the R on the left-hand side of the equal sign, but in our equation, the R is on the right-hand side of the equal sign. Personally, I'm comfortable with leaving the R on the right-hand side of the equal sign. I don't really feel like there's much of a need to bring it over to the left, so I'm going to keep it over here, all right? So that's how we're going to do it. Now, as I mentioned before, if we're solving for R, solve the equation for R. If we're solving for R, that means we're getting R by itself. We are isolating R, okay? Now, what you want to do is get this by itself, which means getting rid of all this other stuff. Now, it doesn't really matter which one we want to focus on, but I do suggest doing one thing at a time. Let's focus on this T. How can we get rid of this T? Because we want the R to be by itself. How can we get rid of the T? Well, we can do the inverse operation. So, in other words, you take a look at what T is doing to R right now. Well, T is being added to R right now. So how are we going to get rid of it? Well, we're going to do the opposite, or we're going to do the inverse operation, which means we are going to subtract T, not just from the right side, but from the other side. So that's huge. You have to remember to do that. You're going to subtract from here. Well, yeah, we're going to cancel, sure, yay, but we got to subtract from here too. Okay, so let's represent that cancellation. That's fine. Now, on the next line, you want to kind of regroup and see, like, okay, where are we now after what I just did? Well, over here, it's P minus T. Now, P and T are not like terms. P and T are not like terms, which means we cannot combine them, which means we are stuck with this. We're stuck with that, okay? And what do we have on the right-hand side of the equal sign? Well, let's see. We have R, beautiful R. We've got the T's are gone, right? That was the whole point of what we just did. And then we have plus S. So now we're almost at the point where we can get the R by itself, but there's still something in the way. There is this pesky, annoying S that no one wants to deal with. So we need to get rid of the S. Well, how will we do that? Well, we're going to have to find the inverse operation. What is the inverse operation? Well, S is being added to R, so we're going to subtract it, not just from the right-hand side, but from the left-hand side. When we subtract it from the right-hand side, these cancel. Now, let's focus on the next line. On the left, it's like, okay, S, T, and P, none of them are like terms, okay? None of them are like terms. So guess what? We are stuck with P minus T minus S, and that equals R, because you cannot combine P, T, or S. So yeah, this is what we're stuck with right there, and that is the answer. Now, maybe the answer in the textbook or in the computer program would be like P minus S minus T. That's fine, but one way or the other, something like this would be the answer. Okay, so solve the formula for the specified variable A equals B plus BCD for C. So what I'm going to do is I'm going to make C red. And go ahead, pause the video, give this one a shot, see if you can do it, and we will meet in a moment. Okay, so let's look at it. I'm going to rewrite it because that's a good idea anyway. A equals B plus B, C, and D. Now the goal, once again, is to get this C by itself because that's what we're solving for. Now the question is, what do we have to do first? We know that we're going to have to get rid of stuff, but the question is, what do we get rid of first? Do we get rid of this B first? Do we get rid of this B first? Do we get rid of this D first? And that's a good question. Now, the bottom line is, there are two terms here. Terms are the algebraic clumps of matter that are separated by either addition or subtraction. So we have addition here separating this algebraic little expression here and this algebraic expression. Now, these are called monomials, by the way. All right. So you have two terms. This is one term, and this is one term. Now, when you're trying to solve for a variable like c, in this case, you want to at least get the term by itself. Now, in other words, since we're trying to solve for c, we want to get this term by itself, which means that this thing has to go right away. That way, we're left with only this term. So since we want to get this term by itself, we got to get rid of this. So how are we going to do that? Well, we're going to subtract that b from both sides. Now, to be clear, it's this b that we're subtracting, not this one, but this one that we're subtracting. And when we do that, these cancel. And let's focus actually on the left, a minus b. Obviously, these are not like terms, which means that we would be stuck with literally a minus b. And that equals all of this stuff because we already got rid of that. So we're stuck with b, c, d. Okay, now c is not quite by itself yet. We have this b and we have this d. Now let's ask ourselves, let's focus on the b. Let's try to get rid of this b. What is b currently doing to this red c? Well, it is multiplying to the red c. That's what it's doing. So guess what? You have to do the inverse operation if you want to get rid of that b, which means we have to divide both sides of the equation, and that means the entire side, each side. We have to divide by this b, and in doing so, we would cancel those b's, okay? Now, what I'm going to do is give myself some room, and we're going to focus on the next line. Now, the truth of the matter is, a minus b over b can actually be left like that, all right? Whenever you have a binomial, meaning two terms separated by either addition or subtraction, that's a binomial, over a monomial, you can just leave it like that. That would be a valid way of representing this entire expression. So we can just leave that there. So that means on the next line, I will write a minus b over b. And that will equal what's left over here. Well, these b's cancel, so that leaves c times d. So that leaves c times d. Okay, now at the end of the day, we still want to get this red c by itself. Well, obviously, we will have to get rid of this d right here. Well, what's d doing to the red c? D is multiplying to the red c, so we have to do the inverse operation, which is, of course, division. Okay, now we're dividing this whole fraction by d. Now, what that will result in on the right is a cancellation. Okay, cancellation. And moving on to the next line, well, let's focus on the right for now. We're definitely going to have c by itself now because the d's canceled, so that's great news. Question is, what the heck's going on over here? The reality is that you have a fraction, a clunky fraction, divided by a monomial here. Okay, so this is a fraction divided by a monomial. Now, there's a little rule that you can use where anytime you have a fraction divided by a monomial like that, you could just rewrite the top part. Rewrite the top part. Nothing changes about the top part, but this bottom part, you could just multiply these two. Okay, so that becomes b times d. So that's a little trick, and I'll give you a pop quiz on that in a moment, so you have an opportunity to try that trick in a moment. But at the end of the day, this is the answer to this problem. Now, I would like to give you a pop quiz on this. Now, imagine we had 3 over 5, and that equaled 10 times x. Now we want to get this x by itself. Now obviously we're going to have to get rid of this 10. So pause the video now, try this yourself, and you tell me, or tell yourself, what x equals after doing what you have to do here. Okay, so hopefully what you did was you divided both sides by 10. Okay, now what does that do? That cancels these. Now we'll focus on the right-hand side. That will give you the x, and that will give you equals. But what happens here? We have a fraction divided by a monomial. In this case, it's called 10. Well, what do? We keep the top part. That's totally fine. And we multiply these numbers, and you end up with 50. So if you got that, congratulations. All right. If you didn't get it, that's totally fine. But maybe rewind it and try it again. Maybe once you've forgotten the answer. Or maybe rewind the entire thing and try this whole thing again. You could always do that too. All right, moving on. Okay, solve t equals m times 9 plus fg for g. So we are trying to solve for this g right there. So go ahead and pause the video, give this one a shot, and we'll meet in a moment. Okay, so first things first, we're going to rewrite it. I'm going to do it over here this time. So t equals m times 9 plus f, and we'll say g, and we are trying to solve for g. So this one is tricky, okay? Some of you watching might be wondering, well, can't I just distribute the m? Because that's what I learned. I learned that, I learned I should distribute stuff. And you know what? I will say, if you were to distribute the m, you could still get the right answer. So there's no problem with that, okay? But I want to actually say that you might want to not do that, because when you distribute the m, you're going to get some weird numbers. It's going to be 9m plus fmg, right? It's just, the m goes into everything, and it's just ugly and clunky. I'm seeing an opportunity to get rid of this m right now, because the truth is that this is just some number, and this whole thing is just some other number. At the end of the day, we want this g to be by itself, and this number is in the way, right? And what's this number doing to this other big number here? Well, it's being multiplied. There's a little invisible multiplication symbol in there, okay? So that means, guess what? We can get rid of the m right now by doing the inverse operation, by dividing everything by m. Cancel, cancel, yay. Focusing only on the left side. The left side is literally just going to be t over m, because t and m are not like terms. They can't be combined. Who knows what they are. Now let's focus on what happened over here. Well, we just canceled the m's out. So that leaves 9 plus fg. Now, you might be tempted to write parentheses 9 plus fg, but at this point, we actually don't even need the parentheses anymore, all right? And in case you're wondering why, well, I'll just write what we're going to. It's 9 plus fg, and I would like to explain why we don't need the parentheses, okay, for those of you who are wondering. The reason is because once we cancel the m's out, the truth is we say, oh, we canceled it, and it just disappeared into thin air. Well, the secret truth is this actually became a 1, and this became a 1, okay? Now, why am I not writing a 1 underneath here? Well, because when you have a 1 as the denominator, you actually don't need to write it. because every number has a 1 underneath it as the denominator. So even though this m became a 1 and this m became a 1 when we canceled, I don't have to write that one. I don't need to write that one. Now, you might be wondering, why don't I write parentheses around this thing with the other one in front of it, Why not? Well, because think about it. If we kept this 1 here and we distributed that, well, what would happen? It would be 1 times 9 plus 1 times fg. Well, that's just 9 plus fg, right? That's just 9 plus fg, and that literally means we don't have to write that one, okay? We don't have to write that one. So, in other words, okay, hopefully I'm not confusing everyone. In other words, after we cancel these m's on the right-hand side, we're left with 9 plus fg. That's what we're left with, so I just wrote that. We're good? Okay, so what did I say before about when you're trying to solve for a variable g, but you have more than one term? You have a term over here, and you have a term over here, and it's separated by addition. Well, what do you have to get rid of first? Well, you have to at least make it so that this term that has the g in it, you want to at least make it so that this thing is by itself. So this one has to go. We got to get rid of this guy. So how do you do that? Well, you ask, what is 9 doing to this term right now? 9 is being added to that term right now, which means we are going to do the opposite, or inverse operation, subtracting 9 from both sides. So when we do that, obviously we will get this lovely cancellation. Now, we're going to focus on this side here. We have t over m minus 9. Now, t over m is a fraction. So it's like a fraction minus 9. So we're going to write the fraction minus 9. Okay? That's important because it's just this fraction minus a 9, so we just wrote that. Then that equals, well, what is left over here? Well, fg is left over. fg is left over. So now we still want to get g by itself. And then the question is, what's in the way of g being by itself? Well, f is in the way. F is a clinger. We got to get rid of this clinger. How are we going to do that? Well, f is currently being multiplied to g. So we're going to do the opposite or inverse operation. I should really call it the inverse, where we divide literally everything by f. And then we cancel. Okay? And let's focus on what that is. Well, we're going to have g by itself. I mean, that's for sure, so that's good news. But then we're kind of looking at this weird debacle here. Truth of the matter is, you can leave it like this. Okay, most computer programs would be happy with that. Okay, would be okay with this. It's just a big mess. It's unavoidably a big mess. All right, so I'm actually going to write that where it's t over m minus 9 over f. Now, another way of writing this answer, in case you're interested in it, is to realize that, well, let's forget this for a moment. Imagine you had 3/5 plus 1/5. Well, I think everyone here knows that you could add these two because they have the common denominator. And what do you do when you have a common denominator? You keep the denominator, but you add the numerators, right? That's what you do. And then you end up with 4/5. Now, most of us are very used to moving from this step to this step. All right. Now, you might not write this out, but you're at least doing it in your mind, and then you come up with the 4/5. So the bottom line is most of us are used to taking this two fraction situation and then turning it into the one denominator thing with addition or subtraction at the top. But what most people are not used to doing is treating this as the first step and then going backwards into this, okay? Because the bottom line is, you could do that. You could say, okay, 3 plus 1 over 5. Well, in reality, I mean, that actually equals 3 over 5 plus 1/5, okay? These are equal to each other. Well, that's what's happening here. You have something minus 9 over a single denominator. So another way of writing the answer, if you wanted to, now you don't have to, but if you wanted to, you could split the numerator, so it's t over m, over f minus 9 over f. You could totally do that, okay? You have subtraction up here, and you could split it apart that way. For the exact same reason that you had 3 plus 1 over 5, that could be split and turned into this. So hopefully that makes sense. Now, if you wanted to go even further, you could then turn that into that whole situation where when you have a fraction over a monomial, well, you can rewrite the top, and simply multiply the two other things, and then you would end up with m times f, and then you could still say minus 9 over f, because that's still there. So that, believe it or not, is another way of writing the correct answer. So we have two ways of writing the correct answer. Now, I have a feeling my student at home probably is going to prefer to just leave it here because, that's quicker. Okay, it's quicker to just leave it there instead of going through the extra steps. I guess the reason I'm showing this to you is don't be thrown off if you see something like this in, the textbook or something as the answer. Just know that this is the same thing as this. All right, so hopefully that makes sense. This is a tricky problem. For my student at home, I would suggest that you actually try this one a few times until you've mastered it, okay? And all you have to do to try it again is rewind the video and pause the video and just try it again. Try it on your scrap paper before I start explaining it, all right? But that's how you do this one. Okay, so this one says solve for D. Well, once again, I'm going to color code it. We want to solve for this blue D, okay? So pause the video, give this one a shot, and we will meet soon. All right, so let's say you paused it, and we'll bring it up here. So we have A equals 6 times pi times D. Now, I think what the teacher is doing with this problem is the teacher is trying to throw you off by giving you pi, right? Because there's this weird pi symbol. It's like, what is even happening here? There's a pi. What's going on? Well, the good news is not much is going on because pi is just a number. It's just a number like other numbers. It's 3.14, blah, 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 okay? Now, it's a useful number when it comes to figuring out what's going on with circles or radians. There's a whole bunch of uses for pi that you're going to learn about later. But for now, it's just a number. It's just a number like any other number. So we're going to do the same stuff to pi that we do to everything else. If we want to get rid of D, we got to get rid of these things. Or if we want to isolate D, I should say. We're not trying to get rid of D. If we want to isolate D, we got to get rid of these things. I strongly suggest only getting rid of one thing at a time. Now, let's focus on the pi. What is pi doing to D right now? It is multiplying to D, so we have to do the inverse operation, also known as division. Okay? Boom, get rid of the pi's. Why not? It was annoying, so we got rid of it. Now, let's focus on this side. When we write the next line, well, guess what? A and pi are not like terms, and they're not reducible. We're kind of just stuck with them. We don't know what A is. We know what pi is, but we don't know what A is, so we are stuck with them. And then we have equals. Well, what's left over here? Well, that would be the 6 and the D. So we have 6 times D. That's what we have. Okay, now, still want to get the blue D by itself, right? We're trying to get this blue D by itself. Well, how are we going to do that? Well, we have to get rid of the 6 somehow. Question is, what is the 6 doing to the D? Well, my student at home, I'm sure, is getting frustrated because my student at home probably knows the answer and is either thinking it, loudly to himself or saying it out loud. 6 times D, well, I just said it, times. That's what it's doing to D. It's multiplying to D, so we have to do the what? Inverse operation. Got to do the inverse operation. What does that do? That cancels. And what does that leave me with on the right? I'm just going to focus on the right now. That leaves me with D, which is fantastic. That's what we want. And it's like D equals whatever the heck this is. Well, remember, we have a fraction over a monomial. Fraction over a monomial. What's the trick? Well, the trick is leave the top alone. Write the top part. The top part is A. Just write that part. What do you do with these things? You multiply them. That's what you do. 6 pi. And then after that, you are done. Okay? You are done with that one. And that's the only way to write that answer, by the way. In the last problem, we had 2 different ways of writing the answer. This is the only way of writing the answer for that one. Anyway, for my student at home, I know this might have been a tedious, somewhat long video. Maybe sometimes I say things that you don't need to hear because you already know it, right? So even though that's the case, I still believe before you take your quiz, you should watch this again. Maybe not the whole thing, but let's just say try the problems again. Okay, just try the problems again, because as you may have noticed, I whited out the answers in all the problems. Now, this one didn't have a multiple choice or anything like that, or it didn't even have really anything, but I whited out the answers. So even if it's just a matter of like fast forwarding to the um, part in the video that just shows the problem, my student at home, I really think you should try the problems again. And I think you should maybe even try them again after that. Okay. Um, Also, on your computer program, you could always try the computer program again if there's a way of resetting it so that your answers aren't there anymore on your computer program. Okay. For those of you who are not my student, this part is probably annoying because you don't know what the heck I'm talking about. But one way or the other, for those of you watching, I do hope that this was helpful. Okay. Once again, it was classifying numbers, rational numbers, whole numbers, integers, blah, blah, blah. And also, we went over literal equations. Literal equations are equations that feature like a bunch of variables, and you're trying to solve for only one variable and isolate that one variable and getting everything else on the other side of the equal sign. All right, so I will talk to you all later. Take it easy.